morning. So thank you for being here. So this is joint work with Prasad and Lalita. So Lalita is here in the audience, and so this has got to do with something called network coding. So you design communication protocol schemes for a multi-terminal network. So if you don't understand any of these terms, no problem. So I'm not going to assume that you know any of these words here. So we'll go slowly. So I'll introduce index coding, and then I'll introduce local decodability, and then we'll move slowly forward. Okay, so this will be our toy example throughout the talk. So you have one source, you have broadcast channel, and then you have 3 receivers. So there are maybe 3 information symbols, or you can think of them as 3 different files which are sitting at the transmitter. So each receiver, so there is this green color, which means that the receiver already has this file in its cache in the local memory. So receiver 1 already has the file x2, receiver 2 already has the file x3, receiver 3 already has the file x1. So if you ask how they got this file, probably they got it during off-peak hours. So let's say everybody was sleeping, the network was not being utilized. So based on some popularity estimation, let's say somebody offloaded these files, a copy of these files at the local memories. Okay. Now everybody woke up, and now it's peak hour, peak traffic duration, and these guys want one file each. Okay. So at this time, maybe you can use this side information to design a communication scheme which can save you bandwidth or time slots. Okay. So the question is, given these green files as side information, how do you meet the red files, the demands? Okay. So there's a naive scheme. You don't do any coding. You simply transmit x1, x2, x3, 3 different packets, one after the other. This guy listens to x1, this guy listens to x2, this guy listens to x3, they download, everybody is happy. Okay. But you're not using the side information, so can you do something better? Yes, of course you can. So instead of transmitting 3 packets, you transmit only 2 packets. So how do you do it? You take linear combinations. So instead of sending symbol x1, x2, x3 separately, you take linear combinations. So you first you compute a function of 2 files, x1 plus x2. You send it first, and then you compute a function x2 plus x3, and then you send. So you are transmitting only 2 frames instead of 3 frames. Okay. But does it work? Of course it does. So let's say this guy, he knows x2, but then he wants x1. So he looks at this linear equation, x1 plus x2. He cancels x2, he will subtract it, then he will get x1 back. This guy, he will take x2 plus x3. He already knows x3, so he will subtract it. Third guy is slightly complicated. So he will take x2 plus x3, subtract x1 plus x2. So he will get x3 minus x1, and then he will add x1 to it, which he already has. So finally, all these guys can be derivatives. So how do you measure how good a scheme is? You need to define what is known as rate. So we will denote rate as beta. So the rate is the number of symbols that you are transmitting divided by the number of message symbols that each receiver needs. Okay. So for this example, you are transmitting 2 symbols in total, because you are transmitting only 2 frames, but each guy needs only 1 frame, 1 file. So you compute the rate as 2 divided by 1. So for this scheme, the rate is 2. The previous scheme, you are transmitting 3 files, but each guy needs only 1 file, so the rate is 3 divided by 1. Okay. So you have achieved a lower rate. Okay. So you have to be careful. So this is more like source coding or compression, and you have to achieve smaller rate, not higher rate. Okay. So rate is defined this way. I hope it's clear. So now the objective is, given a network, the side information and the demands, you have to design a scheme whose rate is as small as possible. And the smallest possible rate you can achieve, we call it the capacity. Okay. And we will denote it as beta opt, the optimum rate possible. This is the capacity. Okay. Now again, remember, you have to make the rate as small as possible, not as high. Okay. So we already saw this. So this is the uncoded scheme. The naive scheme, rate is 3. You do coding, you do index coding, and this is called, and then you have rate 2. And incidentally, this scheme is capacity achieving for this network. So the capacity of the networks is actually 2, and you achieve this rate. So this is a capacity achieving coding scheme. So some few points about index coding. This is very, it's not much here because index coding, there's been a lot of work. It was first introduced about 20 years ago. And there's been a lot of work mainly because index coding is a key and central problem in network coding. The main reason is that if you have an arbitrary multi-source, multi-sync network, you can do some reduction and then you can reduce it to an index coding problem. So if you're able to solve all index coding problems, basically you can solve any network coding problem as well. Okay? So solving index coding problems helps you solve all network coding problems. Okay? And it's also related to wireless communications, something called topological interference management. How do you manage interference in a wireless network? So index coding can be used there. It's also used in what is known as coded caching. For example, maybe it's of use to, let's say, Netflix or other things. Okay? So I'm not going to talk much about that. So I'm going to focus only on index coding. Okay? And this problem is very difficult. So these are some of the reasons why it is difficult. Okay? So the first reason is linear coding schemes are not always enough to achieve capacity. So there are index coding problems where you have to necessarily use nonlinear codes to go close to capacity. Okay? And the usual information theoretic inequalities, what people call Shannon type information theoretic inequalities, they're not enough to prove converses. Okay? So if you want to prove a matching converse, sometimes you need inequalities which are known as non-Shannon type inequalities, which we don't understand too well. Okay? And so it's not non-linear inequalities. No. So Shannon type inequalities, so their origin comes from a simple statement. Conditional mutual information between, if you have, let's say, 3 random variables, x, y, and z, conditional mutual information between x and y given z is always non-negative. Okay? So you plug in x, y, and z, what are random variables you have in your network, and then you can take linear combination of these inequalities. Okay? And whatever inequalities you get, they are called Shannon type. Okay, and these are what people usually use traditionally in information theory. But there are other inequalities which do not arise as a consequence of this. Okay. So you need such type of inequalities which are maybe difficult to obtain to prove matching converse. Okay. So as a result, capacity is, in general is not known. So capacity is known only for some classes of index coding networks. Okay. And again, traditional index coding is channel centric, which means the focus is only on capacity. You have to reduce the number of channel users. Okay. Now let's go back and review whatever we did. So we saw 2 examples, uncoded and coded scheme. So let's go back and look at the capacity achieving scheme. So you're transmitting 2 frames, 3 receivers. This guy wants to decode x1, but he need not listen to both frames. Okay. So because he's using only x1 plus x2, and then he's going to subtract x2, right? So although you're transmitting 2 frames, he needs to listen to only 1 frame. Okay. But also remember that this picture is at the network layer. Okay. This is not exactly the physical layer. It's maybe at the network layer or even above. And although we are using symbols x1, x2, x3, these might actually denote large files. Maybe these are movie files, each one about 500 megabytes. Okay. So maybe you're transmitting 2 500 megabyte frames. Okay. And this guy needs to decode a 500 megabyte file, and he listens to a 500 megabyte transmission. Similarly, this guy, he needs 1 frame, he listens to 1 frame. This guy is very unlucky. The data he needs is only 500 megabytes, but he is forced to listen to 1 gigabyte of transmission. Okay. So this scheme is actually hogging this guy's hardware. You're using twice the amount of hardware duration as required. Okay. So we need to measure this unfairness which index coding induces. Okay. So for that we introduce locality. Okay. So locality is defined as the number of symbols that the receiver needs to listen to or download divided by, normalized by the number of symbols that it actually needs. Okay. So this guy needs 1 frame, he listens to 1 frame, locality here is 1, locality here is 1, locality here is 2, because he needs to listen to twice as much. And then you take the worst case among all the receivers. So you have 1, 1 and 2, worst case is 2. So I define the locality of this coding scheme as this number. Okay, so locality of this scheme is 2. So let's look at some very basic properties of locality. Locality is at least one, irrespective of what coding scheme you use. It follows from common sense, because if I need one frame which I don't have, I need to download at least one frame. Okay? So locality is at least one. Now also recall the definition for the rate. Okay? Rate is number of symbols, total number of symbols or frames in your transmission, divided by number of symbols each guy needs. So the denominator here are same, but the numerator here is upper bounded by the numerator there, because the number of frames that I download cannot be more than the total number of frames transmitted. So R is at the most beta. So R lies between 1 and beta. Okay. So the view we take is this. Yeah.
So the locality, you put time average and improve it from 2 to something smaller.
Yeah. So you got ahead. We'll come back to this in the last. But yeah, absolutely. So you can reduce the locality because 2 guys already have small locality. So you can do time average. So now the objective is you have to design a scheme which has small value of beta, because you want to reduce the total amount of transmission duration, and you want small locality because you don't want to penalize the receivers because of your coding scheme. So this is a rate optimal scheme, capacity achieving scheme. So you have capacity, you achieve the capacity 2, locality is 2 because this guy became unlucky. The uncoded scheme, transmission is 3, locality is just 1. Okay. Now you might ask which scheme is better, this or that. There is no way to compare, there is no fair comparison because they operate in different regimes. So you have small rate, high locality, and then you have high rate, small locality. So you see that there is a tension between rate and locality, so that's a trade-off. So you want to formally characterize this trade-off. So you define the rate locality function. So we define beta star of R. R is some fixed number now. For this particular value of locality, what is the smallest rate possible? Okay. So that we define as beta star of R. Okay. Now, just from the definition, you can infer some basic properties. This function should be decreasing in R, non-increasing in R, because if I increase the value of R, the receivers are okay with downloading more, which means possibly you can achieve smaller rate. Okay, so you have more freedom in designing codes, maybe you can achieve smaller rate. And if R is large enough, if the receivers don't mind getting penalized by a large amount, you can eventually attain the capacity itself. Okay, because the capacity formulation, it doesn't consider locality. So if R is sufficiently large, you can eventually reach the capacity. And also this function is convex in R. Okay, so assume a 2-dimensional plane. So you have R in the x-axis, rate in the y-axis. So if I give you any coding scheme, it has its own beta, its own R. So you can plot it in this 2-dimensional plane. So every coding scheme becomes a point in this plane. So if you have 2 coding schemes, you have 2 points. By time sharing, you can achieve all the points on the line between the 2 points. Because beta star is optimal, it probably lies beneath this line. Okay, so this proves convexity. So we know that it's non-increasing. It eventually reaches capacity. And it is convex, it also means that it's continuous. Okay. So this is a picture I told you about. So you have locality and rate. So here is the uncoded scheme. Locality was 1. Locality wise it was very good, but then it has high rate. This is the coded scheme. It has locality 2 and it had rate 2. And this blue line we obtain using information theoretic inequalities by proving converses and achievability. And this is the optimal curve. Okay. So now you see that the uncoded scheme is actually optimal. Although it looks very simple, it's actually an optimal point on the curve. And this scheme, this achieves rate 2 with locality 2, but as Dr. Rajesh mentioned, so you can do some time sharing and then you can bring it closer to the origin. So in fact, you can achieve rate 2 with locality just 4/3. So we'll look at it sometime later. Okay. So a little bit about locality in index coding. So it's more of a recent idea. It was first talked about by Habib and Langberg, and they did locality analysis for random index coding problems. So you have a bunch of index coding problems, you pick one randomly, and then you try to characterize its rate versus locality tension with some high probability. And then there is recent work by Fraguli's group who talk about locality from a privacy perspective. So privacy issue comes as follows. So let's say you do the traditional index coding without locality considerations. You have some encoding function, okay, which generates your transmitted code word. Now for decoding to happen, the naive way to go ahead is you reveal the encoding function to all the receivers. Okay. Now if I am a receiver and I am very curious, maybe by looking at the entire encoding function, I can maybe infer what the other guy has as side information and what his demands are. Okay. So this leads to some privacy leakage. So to reduce this leakage, they suggest that you have an encoding function, but you reveal only parts of encoding function to each receiver, which means each receiver will be able to utilize only parts of the transmitted code word. So you naturally have a locally decodable index code. Okay. So my talk is very biased. I'm not going to talk about these two works. So probably I will focus only on our work. And okay, so I'll show you. I'm going to basically show you two constructions. They're going to be really simple, but we will need some notions from graph theory, which are again very basic ideas from graph theory. So let's say you have an undirected graph. We will denote it by G suffix U. U will mean that it's undirected. Then its complement GU bar is shown here. So basically whatever edge is not present here, you put it there. Okay. So the edge phi 3 is not present, so you put it here. Edge phi 4 is present here, so you don't put it there. So complement of a graph is a graph itself. We also need two notions, click covering and vertex coloring. Okay, so we'll go slowly. So first I will explain the the left hand side. So assume you have an undirected graph. Okay. A clique in an undirected graph is a subset of vertices which are all pairwise connected to each other. Okay. So if you consider 1, 5 and 2, there's an edge between any two pairs, correct? Sorry, any pair among 1, 5 and 2. Okay. Similarly 4, 3. So it's trivially true. You can choose only 4, 3 among 4 and 3 and they are connected already. But let's say 2, 4 and 3, 2 and 3 are connected, 3 and 4 connected, but 2 and 4 are not connected. So 2, 4, 3 is not a clique. Right? Now the clique covering problem is you have a graph, undirected graph. You have to cover them with cliques. So that every vertex is covered by at least one clique. So I'm covering it with two cliques. One contains this, one contains that. Okay. So in fact the clique covering problem is given an undirected graph. You have to use the least number of cliques to cover the entire graph. Sorry? You can have more than one optimal solution. Okay. Now the same problem can be looked at in a different way if you take the complement. So let's say you take the complement of this graph, you go there. These three vertices are colored by the red clique. So I color the vertices by red color. This is purple, so I color these vertices by purple. And then you see that you pick any edge, the ends of the edge are colored by different colors. Okay. So this is called the vertex coloring. And the smallest number of colors you need to color GU bar is called the chromatic number of the graph. Okay. So essentially these two problems are one and the same. Okay. So we'll basically use only this. Now I will quickly introduce some notation. Again, it's not much, so this is all the notation we will need. So you have in general for what is known as unicast index coding problem, you have n messages, n files, denoted by x1 to xn. There are correspondingly n receivers, rx1 to rxn. Each receiver needs a corresponding message, okay? And it knows some subset of other files as side information. So we will denote it by ki. So this is the subset of files that the ith guy already has in his local memory, which you can exploit to design subcoding schemes. Okay. So I will describe two graphs associated with index coding problem. One is directed, another is undirected. So maybe, yeah. So here unicast means that each message is required exactly at one receiver. But that the problem can be in general, every receiver can demand more than one. Exactly one, yeah. In general, one message could be demanded by maybe 2 or 3 receivers as well. Okay. But instead of doing this definition, maybe I'll show you some example and then it will be clear. So I'm going to define two graphs associated with an index coding problem. So the first one is directed graph. edges are directed, and it's called the side information graph. So if I draw this graph, it means that the index coding problem has 5 receivers, 1, 2, 3, 4, and 5. It also means that there are 5 messages, x1 to x5. First receiver wants x1, second receiver wants x2, so on. And you pick any one receiver, all the outgoing edges denote the side information. So this receiver knows 5, x5, he already knows x2, he already knows x4. So he has 3 files in his cache. Similarly, other receivers. Okay. Now the undirected graph associated with this problem, you draw the same number of receivers and files, 1 to 5. You put an edge between 2 receivers if and only if they know each other's demand. Both of them should know each other's demand. So here 1 and 5 know each other's demand. The arrows are bidirectional, so I put an edge here. You pick 1 and 4, 1 knows 4's message, but 4 does not know 1's message, so I do not put an edge here. Know each other's demand. Okay. So
I know 1 and 5, 1 has 5, it's 5.
in its, yeah,
Then you put an edge.
correct.
What's demand here?
Oh, so the demand is already in the vertices. So you have 5 receivers, 5 messages. 1 needs file 1, 2 needs file 2. So demand is already part of the vertex definition. So the arrows only denote the side information. Okay, so you put an edge here if and only if both the guys know each other's demand. Okay, so this is the simplest scheme in index coding. It's called the click cover scheme. So given an undirected graph, you cover it with cliques. So I'm covering it with 2 cliques. Because it's a click, this guy knows message numbers 5 and 2. This guy knows message number 1 and 5, and so on. Okay, they know each other's demand. Now the coding scheme is as follows. For each click, you send 1 file. So you add the symbols x1, x2, x5, and then you send it. You add x4 and x3 and send it. So the number of transmissions you make equals the number of clicks. So to save in terms of rate, you have to reduce the number of clicks you use to cover the graph. How does decoding work? Let's say you pick receiver number 1. He needs to listen only to this transmission. He already knows x2 and x5, he will cancel. So naturally, locality here is 1. Okay. So again, the rate is, for this scheme, rate equals the number of clicks that you use to cover. And the smallest number of clicks that can be used to cover a graph is called the click hour number. It's again a basic idea from graph theory. So you have IB represented by chi bar. Okay, this is the click hour number. Also, we know that if you take the complement of GU, this becomes vertex cutting problem. And the corresponding number is called the chromatic number of the graph. Okay. So with locality 1, you can achieve this rate. There's also a fractional version of the same problem. If you allow coding over time, then I can do slightly better. So you can achieve what is known as the fractional click covering number of G. Okay. So I will not go into it because this gives you the basic idea. Okay. But if you code over time, you can do slightly better. Okay. So you can achieve this particular rate at locality 1. We also have proof that this is the optimal rate for locality 1. So this slightly, in this slide I'm assuming that you know a little bit about coloring, but I will very quickly go through it. So let's say you have n files in the problem, and these are vectors. Okay, so these are long files of length m over some finite alphabet. Okay. You encode it possibly non-linearly, and then you get a length L file which you are transmitting. Length L over the same alphabet, and then you transmit it. You want locality 1. So the receivers don't listen to the entire transmission, they listen to only parts. Each receiver might listen to different parts. Okay. So pick the ith receiver, he listens to some subset Ri of the L transmissions. You want locality 1, which means the number of transmissions you listen to equals m, the length of the message. So the size of download, they're all equal and they're equal to m. So matching converse idea is something like this. So you can use some information theoretic inequalities based on the demands and coding constraints to show that if you pick any 2 receivers in GU bar, the complement of the undirected graph, then the downloads that they make, they are disjoint. They don't download, there is no symbol that both of them download. So the downloads they make is disjoint. So if you think of R1 to Rn as colors that you associate to vertices of this GU bar, then this induces an L is to M coloring. If you know what this means, I'm very sorry about it. But so that means that the rate that you achieve, L is to M, is at least as much as the fractional chromatic number, which happens to be equal to the fractional click covering number of G. So basically, we now know that if you want the minimum locality R equal to 1, what is the best rate possible? So since we have some more time, I'll quickly go through maybe another construction. So you know how to attack locality 1, but let's say you are, which means you are not penalizing the receivers. So they are downloading only as much as they want. But let's say some receivers are okay with getting penalized. You want R greater than 1. You want some constructions. So I'm just going to show some time sharing construction. Before that, I need to tell you what scalar linear codes are. Okay. So again, you have n files or n symbols, x1 to xn. This is the source. We'll assume that they come from a finite field. Okay. If you don't know what a finite field is, no problem. You can assume that these are real numbers, but the ideas remain the same. So they come from a finite field. You stack them together, so you get a row vector. This is your message vector. The code word is a linear transform of the message vector. It's a linear coding scheme. So you multiply this with a matrix and then you send it. Okay. The receiver decoding operation is also linear. Now remember that the receiver has two pieces of information. One is the code word itself. Another is its side information. Both of these are row vectors. So you hit them with column vectors, carefully designed column vectors. You get two scalars and then you add them together. Okay. Now this is already present in the receiver's local cache. What it needs to download is only C. Okay. Now if there is some entry in DI which is equal to 0, the corresponding entry in C does not take part in this equation. Okay. So you need to download only those entries of C for which the corresponding entry in DI is non-zero. So the number of downloads you make equals the Hamming weight of DI. Okay. So the locality at the ith receiver is the Hamming weight of DI, the number of non-zero entries in DI. So overall, the scheme has rate equal to L, the length of this code word that we denote as small. And the overall locality is the worst case locality, maximum of the Hamming widths of all DI. So this is called scalar linear index coding. Okay, so now the time sharing idea comes from here. So now assume that you have some index coding problem. This is a side information graph, 5 receivers, 5 messages, 4 nodes, messages 2 and 3 and so on. Assume that you already know a scalar linear index code of rate L, okay, but you have no control over its locality. So can you reduce the locality while maintaining the rate? So the way to do it is, first you identify a subgraph, a vertex induced subgraph which is acyclic. So I throw away 1, I keep the remaining. You will see that there are no directed cycles here. So it so happens that if you can find such a subgraph, you can tweak the old code to get a new code so that the rate remains the same, but the locality in these guys is 1, but the locality here you have no control, so take it as the worst case which is here. So if you have a acyclic subgraph which is vertex induced, you can tweak the code to reduce the locality at some vertices but not all. So the easiest thing to do is do time sharing over several such graphs. So you start with some side information graph, you cover it with lots of acyclic subgraph, let's say G1 to Gm, each of them is vertex induced and acyclic, and then you start with a code, original code, for which you have no control over locality, but the rate is known. You have M subgraphs, corresponding to each subgraph you have new code, you tweak the original code, you tweak it little by little, you have M different codes. All of them have the same rate as above, so you are not being penalized in terms of rate. You pick a particular receiver, if it is part of this subgraph, it has locality 1 because of construction, otherwise it has locality. Okay? Now you simply time share between these M codes, okay, one by one. Overall rate remains the same, you are not getting penalized. Now you pick a particular vertex. Now suppose that all the vertices are covered by at least Q subgraph. Okay, so there are Q subgraphs, one on top of each other, which cover each vertex. Then you look at the locality at the vertex. For Q of the codes, you get locality 1. For the remaining, it's at the most L, the worst case, and then you normalize by the number of time shares. So this will be strictly less than the worst case here. So you can get locality, so you can reduce locality without paying in terms of rate. So this is the last slide. So you have this original problem, the toy problem we had. You had 3 receivers, 3 messages, 1 knew x2, 2 already has x3, 3 already has x1. We showed a scheme with rate equal to 2, locality equal to 2. Now you can cover it with acyclic subgraphs. These are the 3 acyclic subgraphs that I use to cover. And then this scheme, if you plug in the numbers, the scheme provides the same rate as above. Rate locality comes down to 4 by 3. And there is a matching converse that shows that this is the optimal scheme for this locality. You cannot go less than 2. Okay. So finally, I introduced you to index coding if you already didn't know about index coding. And I showed that there is a tension between transmitter and receiver. Transmitter wants to minimize the total number of transmission. Receiver wants to minimize the total number of frames that he wants to listen to. So there's this tension, and then we characterize it mathematically. And then although we don't know the exact curve, the full trade-off, we at least know one point now. Okay. So the question is, how do you characterize the entire curve, for which you need strong converse results, and then you need matching achievability results. So that's it. Okay. Thank you. So if you have any questions, I will take. Yeah. We are not using it, and it so happens that you don't have to use it.
So that's because the locality is 1.
Correct. Yeah.
So in the original problem which is happened with the uncoded transition will be the.
So in the original problem, the fractional click covering number happens to be equal to 3. So you had 3 messages. So you had a graph with 3 vertices, and if you draw GU bar, there is no connection between any of them, because no 2 nodes know each other's messages. So the click covering number is actually equal to 3. So uncoded becomes optimal. Okay. We don't know. Oh, so that straight line is only for this particular index coding problem. Yeah, so for this problem we know the curve. We don't know in general.
So in this case, you have this piecewise linear.
Yeah.
4 by 3 point. That's the kind of significant. The code is there.
Yeah.
Give
Yeah.
it to the 4 by 3.
Yeah.
Somehow below that we cannot
We cannot go beyond it.
use all the beta.
Yeah.
So what is happening there?
We don't know. In fact, I think if we had the intuition, probably we could generalize. We don't know yet. So I think we break for lunch. Photograph, so we stay here.